Welcome back to our AI web series, Comprehensive and Intuitive Introduction to Deep Learning. This is going to be season two. And in season two, we will study natural language processing and time series forecasting. We'll start with episode one, where we'll talk about techniques where you can tokenize text. What we have seen so far is a neural network architecture that looks like this. In this neural network architecture, you have numbers going in as input, and then you have one or more numbers coming in as output. Now, what is the problem with this kind of a neural network architecture? The problem is, how do we handle text? Neural networks do not understand text. So the first thing that we need to do is we need to figure out a way in which we take the text and convert them into numbers that can be fed to the neural network. The neural network will take these numbers, emit a number, and from that number, we want to convert it back to text. For example, if you're doing things like a large language model where you would like to generate output, you have to take the textual prompt as input, convert it into numbers, run it through a neural network. It emits a number. From that number, you essentially emit back a text token or a series of tokens. So we have to figure out how do you take text and convert it into numbers so that the neural network can understand it. Because after all, there is something very interesting about text. Text is not some discrete set of words that are just thrown around. Text is essentially a complex arrangement of words that is syntactically, grammatically, and semantically meaningful to humans. So there are some rules that bind these words together, and that those are the kind of rules that you want your neural network to unpack and understand. So what we learn in this episode is basically a technique that allows us to break this long stream of words. You could call it sentences, paragraphs, what have you, into what is called as tokens. And then we'll also look at what do you do with these tokens. You build what is called as a vocabulary. And a vocabulary is nothing but a mapping table that takes a textual token and emits a corresponding integer ID for that token, which is unique. And then it also has a reverse index where you can give it an ID and that'll give you back the text. And then we'll also study a technique or something called, we'll also study what is called as embeddings. And embeddings is basically a technique that allows us to take these tokens and then convert them into not just a number that represents the token, but something much more meaningful than that. Essentially, it is a series of numbers, we could call it a vector, that when you feed to a neural network, it can actually do some really amazing things, which we'll study in episode 2 and onwards. Okay, so let's get started. Let's start with our topic 1, which is tokenization, which is splitting text into individual words or tokens. Okay, so let's first understand the basic, the premise of so let's first understand what tokenization is. So let's say you have a string like this or a text string like this. The cat sat on a mat to play with a ball. Now you run it into a tokenizer, and the tokenizer basically, let's say the tokenizer looks at all the white spaces in between words and he says, at every white space, I'm going to split the word, split the sentence, and each of the words becomes my tokens. Now, after that, you build what is called as a vocabulary. And what you do is that you look at all the unique words or tokens within this tokenized string, and then you construct a table. And a table is basically a mapping between the unique words and the corresponding ID that you give them. You see the first word, you call it the, and you give it an ID 1, and the second word, cat, you give it 2, and so on. And by the way, if you notice, I've actually also change the uppercasing all to lowercasing. You may or may not want to do that. It's very common to do it so that you don't really, the neural network is not sensitive to capitalization. But for us to understand tokenization, it's irrelevant. Just let's go with this that we are going to use lowercase. Okay. So what he did is he took a text, you split it across the white space boundaries, and then you constructed a vocabulary. Then you see the next text, you basically look at the same, you do the same technique, you apply the same technique, and you break it up into individual words. Here you see that the is already there, so you don't add it into your vocabulary. Dog is a new word, so you essentially add it to your vocabulary and assign it the next available ID, which is 11 here. Was is not there, so you essentially add was as well. Already was not there in the first pass while building a vocabulary, so you add that. On was there, so you don't add it, and so on. Then you pass the next string. You essentially repeat this. So essentially, you go through your entire set of sentences in your training data set, and you would build, a table like this. Okay. Now, once we have this table, once you've gone through, literally hundreds and thousands or millions of such sentences, you have your vocabulary and you have your tokens mapped to IDs, you have your IDs mapped back to tokens, correct? So now what you can do is you're given, let's say, you're building a neural network, you give it a text string, you use the same tokenization technique. Here we have used the tokenization technique where you're splitting it across word boundaries. Now that gives you, these tokens. Then from this token list that you have, look at your vocabulary, and then you basically figure out what is the ID for each of the corresponding tokens. So the ID is 1, cat, the ID is 2, plate, the ID is 15, width, the ID is 9, and A, the ID is 5. So you have this. So now you have figured out a way in which you can convert, text to numbers. Now you feed these numbers to a neural network. The neural network, let's say you're trying to predict the next word. Okay. Obviously, we're going to study how do you architect this neural network so that you can predict the next word that comes after the cat played with A. Let's say the neural network is predicting an ID 10, and then you look back at your vocabulary and you say, what is 10? What is the word corresponding or the token corresponding to 10? And you'll say ball. It's okay. I'm going to emit ball. So that's essentially the workflow. Yes. Okay. Now, the first question is, what is the best way to split a sentence into individual tokens? Here I'm splitting it across the white space boundary. Is that the best way to do it? We'll look at that shortly. And obviously, the second question is, what is the best way to convert these, tokens that you have gotten through your tokenizer into numbers that you can pass to a neural network? Is passing the IDs in the vocabulary the right way of, sending it to a neural network? We will see that also as part of this episode. So let's start with the tokenization technique. So first topic is going to be this. How do you take text and break it up into individual tokens? At a very high level, there are two techniques using which you can tokenize. One is called rule-based tokenization. The other is called learned or statistical tokenization. So rule-based tokenization essentially can split words across character boundaries, white space boundaries, or boundaries that even split across punctuation, symbols, and so on. This seems very intuitive. This is very something that you would be able to write in a single line of Python code. But as you will see, this is not necessarily the best, but we'll actually study this, so we actually have a good understanding of this as well. The real way in which real practical applications, whether it is GPT type of LLMs and other neural network architectures like RNN and LSTMs and all those process text, is to use statistical tokenization techniques, which we'll also study in today's episode. So let's start with the basic rule-based tokenizers, understand that and get that out of the way. The first way of doing it is you take an input text. Let's say the input text says, I can't believe how unbelievably fast AI can handle botification. And as you can see, I took a text string which has some symbols like this and all that. It has an exclamation point and so on. So character-based tokenization is at every character boundary, you essentially split and make each character a token. In fact, white space also becomes its own token. So I followed by white space, you can see these are all your tokens. And each of the unique symbol becomes a part of the vocabulary. So you have 21 unique symbols in this. Although you have 68 different symbols, only 21 are unique. So that becomes your vocabulary. Okay, so the pro of this is that, there are only a fixed number of and a very small finite set of characters in any language, and your vocabulary size does not exceed that fixed number of characters. The cons of that is that you're not really capturing any word information. Everything is seen as an independent symbol, a character symbol. So this is not necessarily a great way to tokenize. The obvious intuitive way of tokenization is you tokenize it every white space. You essentially take it, I can't believe, and so on, and you say I is one token, can't is another token, believe is another token. If you do it this way, you essentially say there are 10 tokens or 10 words, and your vocabulary has also 10 unique words. So there's no repeating word here, so the vocabulary also has 10 unique words. The challenge with something like this is that, if we look at, can't, it is essentially taken as one, and there's this punctuation symbol here, but, that you don't know how to kind of break up. So then you say, okay, this is not great. I'm going to actually split it at word boundaries. So essentially I capture every word. If you do it that way, there's a small regex that I wrote in a single line. You can essentially tokenize it, and you say I becomes one token, can becomes another token, and so on. So this is the way in which you can tokenize using some intuitive logic and with a single line of Python code. So what's the problem with tokenizing like this? Because the very natural inclination is either pick this or like the white space tokenizer or word boundary tokenizer. So let's look at a practical problem. Okay, so let's say that these are my training sentences. The football player is playing the play the coach called. My dog runs faster than most runners. Pack your toothbrush and toothpaste every time. Now, if I were to use, let's say, white space tokenizing technique, I would have 21 unique words based on just this input training. Obviously, you're going to have millions of sentences in your actual real life example when you're training. But let's just go with this. We have three sentences, it has 21 unique tokens. Now, let's say that you're trying to use the same tokenizer during inference, which means that, okay, you're trained your neural network using all this data set, let's say for an LLM, and then during inference, where you're trying to predict the next token, you're getting a sentence like this. The sentence is, my dog played ball with her foot. The coach has been running today. I have a toothache, so I brush every day. Okay. Now, if I do the same white space tokenization, what I see is that, in the first sentence, there are there are seven tokens. So is one, dog is two, and so on. I have seven. And when I look at my vocabulary that I've built during training, only 29%, only two of these seven tokens actually are in the vocabulary. Okay. My is there, dog is there because it was here. The rest of them are not there. I just stay with this example. If you see that played, ball, with, her, foot is not there. But as a human, when you look at it, you say that, hey, listen, yeah, played is not there, but there is player and there is play. So shouldn't your tokenizer actually somehow figure out that, hey, I'm going to capture these words as something related to the words that I've already seen. So played is related to player or play. So that's something that you miss out when you do something like this. And if you look at the second sentence, coach has been running today. It has five tokens, and only one of those tokens, coach, is there in the vocabulary based on the training data set that I passed it. The other tokens like has been running every day is not there. Although runners is there, running is not there, and I say, oh, I don't have it. By the way, OOV means out of vocabulary words. Okay, and the same thing goes for the third sentence as well. And here, in fact, this is worse. I have a toothache, so I brush every day. Has 8 tokens. None of them are in the vocabulary. So you have 100% out of vocabulary words. So essentially, now you cannot really do anything. You cannot infer from the neural network because it says I have nothing on these words or these tokens, and I really cannot process it to predict anything. But as a human, when you just look back at your training data, you'll say, hey, toothache, toothbrush, there's something here, and you should be able to essentially utilize those tokens. So let's make one small tweak to this. Okay. And the tweak is, instead of separating the tokens at every word boundary, I will separate them at subwords. Okay. Instead of football as one token, I'll separate it as foot as one token, ball as another token. Player, I'm going to separate it as play as one token, ER as another token. Playing as play as another one token, and inning as another token. So let's say I want to separate them into subwords. How we are going to separate into subwords, we'll study later. But let's say I want to do that. Now, if you look at it in the prior case when I'm doing it with white space tokenizing, I had only 21 tokens in my vocabulary during training. If I'm doing it subword, I have increased it from 21 to 25, just adding about 4 more tokens. But if I were to pass the same sentences in the prior example into the inference, now I can see that the overall out of vocabulary is only 56%. With white space tokenization, it's 85%. So there is actually a big improvement, even with a very, very small training sample set like this. Just by splitting at subwords, I have increased the probability of finding a token in my vocabulary. And what that means is that during inference, I don't throw an error saying that, hey, I've not seen this token, I don't know what it is, and as a result, I really cannot process it. So there is a benefit, as you can see, that if you move from white space or word boundaries into subwords, there is a big benefit. But the question is, how do you do that? And that is where you go from the rule-based tokenization, which is essentially a rule says split out every white space, into what is called as learned or statistical tokenization, which is a very fancy way of saying I'm going to split at word boundaries. Okay. All right. So now at a very high level, let's look at the different phases in which you can do statistical tokenization. The phase one is training, where you take lots and lots of text, you do an entire web crawl or whatever you have, and you essentially clean it up and then you extract sentences from that and you pass it to your tokenizer. And the tokenizer actually emits 3 things. First, it will emit a vocabulary that we have seen, which is basically a collection of all the unique words that it has seen in the training data. And those words are not full words, they are subwords. The second thing it does is it builds an index so that, if you give it a token, it will give a corresponding unique ID for the token, or which is used during feeding into the neural network as an input. And it also gives you an inverted index where, given an ID, it will give you back a textual token, which is required during the output part of a neural network, where when the neural network predicts an ID, you want something to reference back and get the corresponding word or token from that. So that's a reverse index. So, and the third one is what is called as merge rules, okay, which is going to be used for splitting or tokenizing during the inference stage. Okay, so the first stage, training, takes a lot of text and builds these three things: vocabulary, index, and merge rules. So now when you're doing inference, you essentially pass in whatever text string or sentence or paragraph, the tokenizer takes it. Now it looks at the vocabulary that it's built in the index and specifically these merge rules, and it figures out how I have to break this incoming text into subwords. And the goal of this is that you want to minimize the number of out of vocabulary words so that you can essentially infer with your neural network. Okay, so let's try to understand the subword tokenization techniques. The gold standard for that is what is called as Byte Pair Encoding, BPE. It's a state-of-the-art tokenizer, and it has become the dark horse of natural language processing. And for example, if you look at the LLMs like GPT and Grok or DeepSeek and all that, they all use BPE as the tokenization technique. Okay. Now the interesting thing is that BPE itself was published in a paper in 2016. But the interesting thing is the idea is borrowed from an article that a guy called Philip Gage wrote in the C Users Journal way back in 1994. And this idea that he proposed was actually an idea for doing data compression. Actually, let's kind of look at the inspiration for BPE and then we'll go into BPE directly. And the idea was that, let's say you have a set of text like this, set of symbols, set of characters. So what he observed is that there is repetition of certain symbols. So he said, okay, if I substitute the repetitive symbols with some other substitute symbol, then I can essentially compress the string, further. So for example, if you look at this, I will look at all the unique symbols. So there is A is one unique symbol, B is the second, C is the third, and D is the fourth. So I have four unique symbols. And I will say, okay, A represents A, B represents B, and so on. Now I can look at the subwords and say AA is repeated twice. So I can actually make this its own symbol, and I can string the text down instead of it being AAABD, I can call it ZABD. And then I add a new symbol to my vocabulary called Z. And whenever I see Z, it actually means it's AA. And you can keep on doing this for the same sentence. You can say, oh, there's another token here or another pair of tokens here that are similar. So I can essentially substitute them with something else. Let's say we call it Y and add that Y to my vocabulary. And whenever I see Y, it essentially means it's AB. And I keep on going this way. I see that ZY is basically repeating. So I can say I can merge ZY into its own unique symbol, call it X, add that to my vocabulary. So this is the technique that was used to compress strings. And it's very intuitive, very simple to understand. It's all great, but what has this got to do with text tokenization in NLP? So BPE essentially borrows the idea from this. So what does it do? What is byte pair encoding? You already see from this, the way it is labeled or named, there is pair. So there's something about pairing here. Let's try to understand this. So let's try to understand the BP algorithm using a string like this. Pat, pat, cat, sat on mat, cat sat on mat with pat. Obviously, it's a nursery rhyme, and the reason I chose something like this is because it's a very simple small words, and it allows us to kind of focus on the algorithm rather than the complexity of very long words and so on. So the first thing is I'm going to convert this into lower cases, and one more thing I will do is that I'll also maintain this white space. Right, I'm using this Unicode symbol, this empty white box, to represent that there is white space. So take a sentence, and again, I can use white space tokenization, and I can just break it up. I break it up into individual words like this. And I capture that, pat ends with a white space. I capture that here as well. Okay. So that's the first thing. The second thing I do is I'm going to take this input now and I'm going to break it up and split it up into every character boundary. So this one, PAT white space becomes P, comma, A, comma, T, comma, this white space, and every word I'm going to do this. And then I'm going to build my initial vocabulary. And the initial vocabulary is going to have only the unique characters. So these are the only unique characters in this entire sentence. So this gets added to my initial vocabulary. Notice that even the white space is added to the initial vocabulary. The next thing I do is what is called as merging. And this is the crux of BPE. So let's try to understand this. So I have my tokens. This is merge. I'm merging for the first time. These are my tokens. What I've done is I've split them at every character, and I've built my vocabulary based on every character that I've seen, unique character that I've seen. Now I'm going to find out what are the pairs in all of these, tokens. What I mean by pairs is if you look at pairs as two things, right? So P is one, A is another, A is one, and T is another, T is one, and the white space another, and so on, right? So I can say PA is one pair. How many times does PA appear? It appears one, two, let's go down here, three. So three times it appears. I'm saying this pair appears three times in my sentence. Then let's look at the next pair, AT. How many times does AT appear? One, two, three, 4, 5, 6, 7, 8, 9. So 9 times. And T and white space also appears 9 times. And then you go to the next one, which is again P and A, appears 3 times. You already captured that in our paired list. So we want to keep that. Let's go C and A. C and A appears only 2 times. So this pairing appears at here once and then here once too, right? So essentially, I have created a co-occurrence of adjacent tokens, which we call as pairs, and then we compute the frequency or the number of times those pairs appear in my sentence. Then I'm going to sort them. So I'm going to find out what is that pair that appears the most frequently, and I find out that AT appears the most frequently. So does T and white space and so on. But I'm going to pick, let's say, just the first pair that appears the most. Now I'm going to merge them. Remember what we did, what we saw in the compression algorithm? He finds out symbols that are repeating and then he merges them and creates a unique symbol and adds that to the vocabulary. We're going to do the same thing here. So I'm going to merge A and T into its own symbol called H, and I'm going to update my token list by just merging them. So it was P, comma A, comma T, comma white space. AT is merged. So I'm going to, wherever I see A, comma T, I want to merge them. So that becomes one token. Instead of instead of one individual character, it becomes a joining of two characters, making it one token. Correct? And then I also update my vocabulary by adding this merged pair at the end of my vocabulary. Okay. Then I create something called as a merge rule, which is nothing but a list. And this list basically says what I have done is in this first iteration, I have merged A and T into one symbol called A. Now, this merge rules is very important. The order in which you kind of merge is also very important. But just for now, just go with the flow. There is something called merge rule. Okay. So with this merge rule, let's go back and run another loop on this same sentence and then figure out what other pairs I can merge like this. Okay. So let's say in my merge 2, I'm going to say, by the way, when you take after the merge, you have merged these two things, these two characters. So if you essentially want to create a pair, you're going to create a pair with P, comma, AT. That's your pair because now this is one symbol, right? P is one symbol, AT is another symbol. So you merge, you essentially create a pair like this. And you create all these pairs. Like in the past, you're going to sort them and figure out what is the pair that has the highest frequency. You see that AT, comma, white space has the highest frequency. So you're going to merge and make that one subword. So now when you make it one subword, you basically add it, you go to your token list and update your token list by merging them, like you merge them from AT, comma, white space here to AT white space is one token now, correct? And then you add this new thing into your vocabulary, and then you add to the merge rule this new rule that you've added, okay? And you essentially add it to the tail of the merge rule because the order in which you're merging is very important during inference. So you just add it to the tail. Then you go back and run it again. Now you're going to say, hey, this is a token list and I'm going to figure out the pairs. I'm going to figure out the pairs that occur the most. I'm going to go merge it. Pat followed by white spaces the most frequent. So I'm going to merge that and I'm going to make it one word. Now we can see that pat followed by white space itself made it into the vocabulary. When you started, it was not there, but now that entire word made it into the vocabulary, correct? And your merge rule, essentially, you get this new merge rule that you've added. I keep on doing this again and again and again till you're left with no more pairs to merge. Or you basically say, I want to bound it to a certain number of merge loops that I would like to run, 10,000 loops or whatever it is. At the end of this, you essentially have processed one sentence and you have built your vocabulary and you also build your merge rules. Then you pick up the next sentence and you run this, and so on. Now, this seems like too cumbersome, but believe me, this is the gold standard way in which you tokenize. And all the LLMs essentially use techniques like this. There's another technique which we'll study called WordPiece tokenization. But BPE is a very, very common and one of the most popular tokenization techniques. So it might seem very cumbersome, but it is great because what it is doing is that it is trying to identify what are the subwords that actually appear many number of times in your text, and it takes those subwords and makes them part of your vocabulary. So, for example, if you had words like running, runner, and so on, the run part is common here. That's a subword. So, it actually takes run and also adds it to the vocabulary. So, whenever you see something like runs, right, it'll again during inference time, it's going to split that runs into run and followed by an S. Or it'll say, oh, run, I've seen this in the vocabulary. And it's going to basically say that it's a word that it is in my vocabulary. It's not an out of vocabulary word. Okay. So that's on the training side. You have seen the training side. And now that we have built all our merge rules by parsing all the sentences in our training data set, let's look at what happens during inference. Okay. So by the way, after the merge rules and after the training is done, this is my vocabulary and these are my merge rules, right? Okay. Now let's say that during inference I get text like this: Pat sat on mat with cat. Again, I initially do the prep work by splitting the words across these boundaries, and I do the same thing. I take the first word and then I basically bring it up into tokenize it using every character. I create a set of pairs, P-A-T and T followed by white space symbol. With this pairs, I will look at my merge rules, and I'll look at the merge rules in the order in which they appear in this list, and I'll figure out how to merge them. So P and A, is that there somewhere? Okay, let's see. P and A is not there anywhere. Okay, good. Then I'll look at A and T. Is A and T anywhere? Yeah, it is actually here. So first thing I'll do is I'm going to merge A and T. Originally it was like this. In my first merge, I'm going to merge it this way. Then I again create separate set of pairs, right? Or new set of pairs, which is P comma AT is one pair, AT comma white space is another pair. Now I'm going to look at, does this pair exist in my merge rules? P comma AT. This is not it because there's P comma AT white space. So it's not this. It's not there. Okay, what about AT comma white space? Actually, AT comma white space is there. Good. So what does AT comma white space merge into? It merges into this symbol with, or this token with three symbols. I want to do the merge. Then I go and merge that, and then again I split it into pairs. Here there's only two pairs, P comma AT white space. Now I look at my merge rules again. Is this pair merged? Yes, it is merged here. It's merged to Pat. So essentially, I take that and merge it this way. Now, obviously, this seems like, okay, what are you really trying to do here? It almost feels like, you're going through all this extra computation to get back at exactly the same thing that was there in the, in the input symbol or input text. But that's not the case. Actually, what happens is that this is a very trivial, simple example. When you have a very large corpus of data, you will actually notice that using this technique, you will be able to extract, right, all the subwords without writing any if then else statements. And then during inference also, you'll be able to extract the same subwords, and then you'll be able to look them up in your vocabulary, and you get a hit in your vocabulary. Okay, so this is byte pair encoding. Seems kind of weird at first glance, but as I said, after numerous types of proposals, this turns out to be the gold standard that most people use. I mean, there are certain variances to this. For example, there's a variance called WordPiece tokenization. And the strategy behind WordPiece tokenization is that, it basically says, hey, while BPE looks at merging words that appear the most, it essentially looks at frequency of appearance of the tokens to merge. WordPiece basically says, I'll not just use the frequency, I'll try to merge those words that help me predict the surrounding words better. And essentially, it's nothing but you give it a score for every pair, like we saw in BPE. Instead of just looking at the frequency of occurrence, you'll also basically you'll give it a score, and that score will tell you whether you want to merge or not. Those that score the highest, using the scoring function, I'm going to merge. And in literature, when you look at WordPiece tokenization, you essentially see that WordPiece tokenization depends the subwords, the second part of the subword, and so on with this pound symbols. So you know that it's a continuation word. It's not a token by itself, right? So if you have things like skate, it would actually tokenize it into skate. Skateboard will be tokenized as skate, comma, a continuation of board. Skateboarding will be tokenized into three tokens. This one single word will be tokenized into three sentence: skate, followed by continuation board, followed by continuation ing, and so on. So during inference, let's say you were to get skater, it would immediately extract the subword called skate and then the continuation of er. And then skate, it's already found in the vocabulary, it's going to use that. The last, r might be found through other, words which are also split in similar ways. Right? Let's say biker would also have the same continuation symbol. So you would also find that in the vocabulary. Snowing would be split into snow and ing. Ing is also there in many other words as suffixes. So you'll also find that snowsuit will be a snow and suit and so on. But as you can see, right, techniques like this allow you to take large sentences and then essentially run them through this splitting and merging techniques to extract all the subwords out of them. Yeah, there are again several other types of techniques. SentencePiece is another technique. There is a thing called byte level BPE, which operates directly on raw bytes of text rather than characters. So it actually is very beneficial in not just tokenizing human text, but also things like Unicode symbols like emojis, for example, and whatnot, right? And by the way, if you look at the popular LLMs, GPT-1 use the standard byte pair encoding technique, whereas GPT-2 onwards they move to this byte level BPE, right? BBP is what it's called, because they wanted to go and consume vast amounts of human generated text like tweets and all that which have these emojis in it. So essentially the technique is the same. Instead of using character based things, they use byte based splitting. Google's Gemini uses SentencePiece. Grok uses BP, byte level BP. DeepSeek uses BP. So pretty much as you can see, right, most of them use BPE as their tokenization. So you just need to know that when you're doing your projects, you're going to be using BPE. Okay. Now I'm going to show you how you're going to use libraries, open source libraries to tokenize. There are several libraries that you could use. Hugging Face has a very popular tokenizer. There are tokenizers like Spacey and LTK and so on. But before I get into all that, let's actually see a demo. Okay, so let's use this interesting web tool to see how different large language models actually end up tokenizing input strings. So I'm going to use this test string. I wake up with a toothache and brush my teeth with a toothbrush and toothpaste. So if you look at GPT-2, it basically tokenizes it as follows. Right? I wake up as, I wake is one token, I is one token, wake is another token, and so on. But when it comes to toothache, it actually split tooth and ache into two different tokens because it has found out that tooth is a subword that can also use, in other places, like for example, toothbrush and toothpaste and so on. If you look at, let's say, a llama, right? What llama does is it basically looks at it and it might do the same thing. And if you look at, let's say, DeepSeek, it does the same thing. Now let's look at, let's say, Google. Google is basically doing something different. It basically is extracting tooth, but it also extracts toothbrush and toothpaste as its own individual tokens. Why do you think it's doing it this way? The reason for that is, while BP is a algorithm that we talked about, there are some optimizations that each one essentially applies. For example, one optimization that you can think about is when you're merging a pair, I only merge the first pair that has the highest frequency. But you can look at all the other words that have similar frequencies and merge them, in one shot, right? Then your merge rules will start to look differently. And sometimes what they also do is that there are some common words that kind of make sense to keep them together as one word, like toothpaste, toothbrush, and all that. So they might also directly add it to the vocabulary. And as a result, you would see the tokenization happen this way. Now let's go and look at how to use different open source libraries so that you can get started with tokenizing text to do your NLP projects. So let's start with the first demo. So here I have a Google Colab notebook. And what I wanted to demonstrate here is the various open source libraries that you could use to tokenize your input text for your NLP projects. Obviously, you could hand code your own BPE, which I have done, but I don't think it's necessary to do it. You can essentially use many of the available open source tools. So let's do the following. So in this, the input text that I'm going to use for our demo is, I can't believe how unbelievably fast AI can handle portification. Okay. And I'm going to just lowercase it. That's not needed, but I'm going to lowercase that raw text into the text. Okay. There are some utility functions. We can skip that. Well, what the utility functions do is that it mounts my Google Drive because I'm using Google Colab and it has my Hugging Face token here. It loads that and it also, generates a vocabulary and all that. We can ignore this for now. All right, so actually let me run it, but we can ignore that. All right, so let's look at the basic tokenizers. The basic tokenizers, as we discussed, essentially is to tokenize based on white space. We said it's not really that useful. Tokenize based on splitting it into word white space boundaries. Simple code to do this, and simple code to build a vocabulary, or using a regex to do it based on word boundaries and so on. We already demonstrated this is not the best way of using tokenizers in the NLP projects because they don't capture subwords. So let's look at a few popular libraries. So there's a natural language toolkit library here. Then there's this very popular library called Jensen. There's a library from Hugging Face. There's a library called Spacey, and so on. So let's look at, for example, Jensen. In Jensen, I've already installed the Jensen, library. So I'm not going to run that again. So what I do here is I'm going to take the text, the raw text, and pass it through this library utility called simple preprocess. And what Jensen will do is that it's going to pre-process. It's a rule-based, not a learned or a statistical tokenizer, but a rule-based tokenizer. And it basically says, hey, listen, your I can't believe how fast AI can handle bottification. Essentially becomes can believe how unbelievably and so on. As you can see, it has taken out some of the more common what they call as stop words. I, for example, is taken out, so on and so on. So that's one way of tokenizing. The benefit of something like this is that it is rule based. It does not have to go through this merging and all that. So it's typically very, very fast. In some projects, you might want to use something like this. Okay, so that's Jensen. Now let's look at Hugging Face. This is a very popular tokenizer. And what Hugging Face has is basically it has the byte pair encoding. It also has WordPiece encoding and so on. So I have mounted my Google Drive. So I've taken the Hugging Face token from there. Okay, now I'm going to use the GPT-2 tokenizer that Hugging Face provides. Okay, and I'm going to run the same sentence. Okay, let's run that. By the way, what I do is that I pass that through something called GPT-2 tokenizer from pre-train. That becomes a tokenizer object. And then I pass the raw text to that and use the tokenize method from that, and it gives me all the tokens. Okay. So as you can see that I can't believe how fast AI can handle bottification is tokenized into I can followed by apostrophe T, believe, how, unbelievably, and bottification is split into per, and T is another subtoken, ification is another, and so on. Now you'll also notice that it has the special symbols against some of the tokens, not all of them, but some of them. It's basically a way in which in a way in which GPT actually tokenizer captures, that this is the beginning of a new word. For example, you don't see this as apostrophe T because it's a continuation of the word that precedes it. Okay, that's how they do it. That's the reason why you see the special symbol here. And these are the token IDs, corresponding token IDs. Because in your NLP project, you would like to go from, of course, take text and tokenize it, but you also want to know the IDs associated with these tokens. So you can use the convert tokens to IDs and it will give you all the IDs for the tokens. Okay. Then you can also use the Hugging Face WordPiece tokenizer. It's very simple. We can call auto tokenizer from pre-trained word based uncased, and then you do this and it basically goes through the WordPiece tokenizing algorithm and it will split the incoming sentence into I can becomes one token, this apostrophe becomes another token, T becomes another token, believe, how, un becomes another token. Kind of makes sense because un is a very common prefix in English, and the continuation, hash bell is another one, and so on. So there's a different way in which it is tokenized. As you can see, different algorithms tokenized in different ways. As long as you're using the same algorithm to tokenize during training as well as inference, it is fine. Another very popular algorithm is called Spacey. Now, Spacey is not a statistical tokenizing algorithm. It is a rule-based tokenizing algorithm, which means that it has a bunch of rules, and they've gone through the exhaustive set of rules that they have built over time. For example, prefix rules that basically say if you see a currency symbol followed by a number, then you should separate the currency symbol and the number as two different tokens. And happy followed by a period should be happy, and then a period is a separate token. There's a thing called infix rule that says 3.14 will remain as 3.14. It's a value for pi and so on, right? So and so on. And people use Spacey quite commonly if they don't want to go through this whole trouble of creating sub tokens and all that, right, that you see with BERT. So as you can see, there are different ways in which you could tokenize. Let me just do this. You could use for extremely basic projects You can use, white space tokenizer. I wouldn't recommend it, but you could if you want. Or you could use NLT case or GenSim library or Spacey if you want to use rule based. Or you want to go down the path of the more cutting edge BPE tokenizer, then you would use the Hugging Face tokenizer. I would recommend going with BPE based tokenizer. Now, for our second demo, what we will see is how we can use the Hugging Face GPT-2 tokenizer and how can we add new tokens to that tokenizer so that you can use this tokenizer in your NLP projects. So the first thing that I'm going to do here is I'm going to download the GPT-2 vocab as well as the merge files. Remember that this is basically based on the byte level BPE algorithm. Okay, so I've downloaded that. Next thing I'm going to do is let's actually just look at the what is there in the the vocabulary for the GPT-2's tokenizer. So these are the different words that are there or tokens that are there, and these are the corresponding IDs for those tokens. All right. Now, what we'll do is that we're going to see what happens when you give it a text string, because in your project, NLP project, you're going to give it a text string and you really wanted to tokenize it without you having to implement all the BPE, right? So let's assume that this is your text string. You will essentially call tokenizer.encode text and then extract all the tokens. So you would run this and you'll see that the runner runs with dog running along with other runners is tokenized by the BPE tokenizer of Hugging Face as the and runner and runs with and so on. The another sentence I give here is the runner can't be running when the dog doesn't run. It basically said the is one token, runner is another token, can't is split into can and apostrophe t as another token and so on, right? This is what it does. Okay, now what we want to do is want to do an experiment where we want to see what happens when you pass it some string where it has not seen those tokens before. GPT has not seen those tokens. So let's say that, I'm passing the string. Let's add some seemingly new words like Partha, Sitala, Cube, Cuttle, and so on. Now, it's very unlikely that it has seen this word or these two words in its vocabulary. Cube, Cuttle, maybe it has, I don't know, maybe it's not. 3.14, which is the value of pi, and so on. So what really happens? So I wrote this small utility routine called extract unknown tokens. All it does is that it takes this sentence, runs it through the Hugging Face tokenizer, and then it checks if that token exists in the vocabulary or not. That's all it does. So let's just run this and see what happens. So when you run this, okay, let's basically becomes let as one subtoken and then apostrophe is another token and so on. But when it comes to, for example, my name here, Partha Sitala, it does not know that, there is a this basically Partha is actually one word. So it basically splits it into subwords. Par is one subword it has split it into. Maybe, because paragraph is another word that starts with par. So Partha, right? Also has the same subword in the beginning. So that's the reason why it split it like this, right? Now, this is not ideal. I don't want really it to split it like this. I want it to retain Partha as its own word, Sitala as its own word, and Kubekatla as its own word. So how do you go about doing that? So what I'll do here is I'm going to run this sentence and let's see, again, I'm going to print unknown tokens, which is what we already saw, but I'm going to print it again. And then I'm going to add words to this vocabulary and tell this tokenizer that, hey, going forward, I want you to treat these as words themselves. I don't want you to kind of split them into subwords. So the way you do that is you give it the set of words that your tokens that you would want them to be treated as individual tokens, and then you use this add tokens method. So let's run that and see what happens. So before I add, so the first thing I'm doing is I'm printing it. As you can see, Partha Sitala is split like this. Cube Cuttle is split even in a more terrible way. K is its own subword, UB is another subword, and so on. But now when I add the things, right, after adding these new tokens, you can see that, Partha got added as it is, and a new ID has been assigned. Sitala is added as it is, another ID has been assigned. Kubekattle added, another ID has been assigned, and so on. So this is how you would use your Hugging Face tokenizer or other tokenizers too that we saw in the prior demo. Now let's go back to our presentation. So what we have seen so far is this, which is how to solve this problem of taking a text input and then breaking it up into tokens. Yes. The next thing that we're going to look at is what we call as embeddings.